Gravimetric analysis is a common technique used by chemists in the laboratory. What they'll do is they'll selectively precipitate out a particular element in order to determine the mass of that element in a sample. Sometimes the sample is pure, sometimes the sample is an unknown impure mixture of things. But we can see in like a larger picture how that information would be important. Say you're a soil chemist and you want to know how much nitrogen is in the soil. So you would selectively precipitate out the nitrogen, and then you would be able to calculate the mass percent of nitrogen in the soil. Similar technique can be used for water samples or any kind of samples. We can precipitate out what we're interested in and then use stoichiometry to determine how much of that element is in our sample. So we're told in multiple places in this problem that we're interested in the amount of chloride in the sample. Up here in this first sentence, it says, straight out says, it's a gravimetric chloride analysis. And then at the end, they ask us to calculate the percent of chloride in the sample. So we definitely want to figure out the mass of chloride. What information are we given in order to figure all that out? Well, the fact that the whole sample had a mass of 0.1567 grams is not too important at first. We use that to calculate the mass percent. But I do want to hone in on the fact that they obtained 0.2516 grams of silver chloride. This is the precipitate, and so that's important when we write our balanced equation as well. We want to clearly identify our precipitate. So we were given the mass of silver chloride. First step, let's figure out some kind of balanced reaction that's going to relate the chloride to the mass of silver chloride. So for certain, since gravimetric analysis involves precipitation reactions, we know that silver chloride, solid silver chloride, is our product. And chloride has to be a reactant because that's what we're interested in. And in this particular technique, they used silver ions to cause the chloride to precipitate out. So we'll do Ag+. This reaction's balanced. The other thing we know is that, and this is how the technique goes, you're gonna put in an excess of silver ions. So we keep on adding drops to our solution until solid stops forming. Sometimes it's a little bit hard to see, but on this particular one with the silver chloride, you actually, it no longer gets cloudy. So you can add a couple of drops of maybe silver nitrate and nothing happens, and then you know that you added enough of the silver ion. So now that we have a balanced reaction, we can work towards relating these two pieces of information, the one we want and the one we're given. So I'm going to start with the number we were given, the amount of precipitate. And since it's in grams, our first step will be to convert it to moles. So using the molar mass of silver chloride. Alright, after that, always, just like with all the stoichiometry, look at what we got rid of, look at where we're going. So the grams of silver chloride will cancel with the grams of silver chloride. Now, since I'm interested in chloride ions, and I have moles of silver chloride, I can get rid of the moles of silver chloride and relate it back to chloride ions. How do I know that it's a 1-to-1 ratio? So there's two different ways that I know it's a 1-to-1 ratio. One, I can look at the formula here, and I know for every mole of silver chloride that forms, we must have 1 mole of chloride in the unknown sample. I can also look at the coefficients of the balanced reaction here. We have a 1 in front of chloride and a 1 in front of silver chloride. So either by the balanced reaction or the formula, we're going to establish this relationship. And then let's take it one step further because we want the mass of chloride. So I'm just going to grab the molar mass, and it's just going to be of chlorine. The fact that it gained an extra electron is not going to impact the molar mass. Remember, the electrons have negligible mass. So I'm just going to use the value off of our periodic table. The other thing is, I know as an element, chlorine will exist as chlorine gas. But we're not talking about diatomic chlorine here. We're talking about chloride ions. And so they're just going to be single ions. And I haven't been following my units. So let me back up for a second and look at how the units are canceling. So moles of silver chloride cancel moles of silver chloride. Moles of chloride cancel moles of chloride. And I'm just left with grams of chloride here. When I did this earlier, I got 0.0622 329 grams of chloride. No, it's hard to see numbers on that side of the board, but I'm going to rewrite that number for our last step. So we weren't asked to calculate the grams of chloride, we were asked to calculate the percent of chloride in the sample. And with gravimetric analysis, I'm going to interpret that to mean mass percent. Mass percent is going to be the same kind of formula that we use for all our percent formulas. Part over whole times 100. So the part is going to be the answer that we just got. That mass of chloride. And then the whole is going to be the mass of the sample before they started working it up. So as part of the workup, like if it was a soil sample, you would dissolve it and you might filter it. But before they started processing it and working it up, they had 0.1567 grams of whatever. Grams will cancel grams. Your units always have to cancel on a mass percent. And then we're just going to multiply by 100. So that means that this particular sample contained 39.71% chloride by mass. In problem number 2, we're asked to determine the amount of calcium carbonate in a piece of sidewalk chalk. Now the chalk is not going to be pure calcium carbonate. Calcium carbonate doesn't hold together all that great, and sidewalk chalk obviously comes in different colors. So there must be other things like maybe some kind of adhesive or glue and dye and who else knows what else. But there's a bunch of other stuff in the sidewalk chalk. But our goal here, we're going to take advantage of the reaction of calcium carbonate with hydrochloric acid that produces carbon dioxide. We're going to take advantage of that reaction to determine what mass or what percent of calcium carbonate is in our sidewalk chalk. What I've done here, since the sidewalk chalk is impure, I'm going to ignore the 3.28 gram value for now. I'm going to save that for the very end when we got to do the mass percent calculation. However, I can use the volume and molarity of hydrochloric acid to calculate the moles of hydrochloric acid. And I can use the mass of carbon dioxide to calculate the moles of carbon dioxide. Since there's so many different questions associated with this particular problem, I'm thinking that my best plan of attack will be an ICF table. So now that I have the mole values, I'm gonna set up my ICF table. So first things first, on my initial line, if I'm thinking about what I was provided and where I wanna go, the whole goal of this problem is to figure out the mass of calcium carbonate. And so I don't know, I'm just gonna put a big question mark here, but I don't know how much calcium carbonate I started with initially. That's what I'm trying to find out. I do, however, know how much hydrochloric acid was added, and we converted that to moles. So I'm going to enter this in my ICE table as a mole value. Calcium chloride initially, remember on your initial line, it's going to be a 0. It hasn't started forming yet. Neither has the water or the carbon dioxide. So those will be zeros. And that's true for the products on any initial line when you're setting up your ICF tables. The C line takes into account the coefficients of the balanced reaction. We're going to use up our reactants, and since there's a 1 out front that's understood, this is going to be minus 1x. The minus means we're using it up. We're going to do a minus 2x on our hydrochloric acid. And then since we're producing these things, we're going to do pluses. And there's a 1 here, so we'll do plus 1x plus 1x and plus 1x. Now, looking back at the wording on this problem, it said that when they added the hydrochloric acid to the chalk, it yielded 0.981 grams of calcium carbon dioxide. Yield means produced. And I'm interpreting that or taking that to mean that's how much carbon dioxide came out at the end of the day. So that value belongs in my final line. I'm going to grab the mole value from the previous board here and not use the grams, but that's where it came from. So for carbon dioxide, I'm over here, I'm going to do 0.02229 moles. So typically, once we've filled in the initial and the change lines of our ICF table, and it's eliminating excess reactant problem, we set both of our reactants equal to 0 and we solve for the smaller x value. Here, well, there's a couple issues. One, they already told us that the hydrochloric acid was in excess. And therefore, by design, the calcium carbonate was our limiting reactant and all of it was reacted. But we don't have complete information about calcium carbonate. So we can't use the calcium carbonate column to solve for x, right? We could just have a big question mark up there. However, over here, we do have a complete column for carbon dioxide. And we know that the ICE table works so that the initial line and the change line add up to the final line. So 0 plus 1x equals 0.02229. So by this column being complete, we know what our x value is. X is equal to 0.02229. Water and calcium chloride all have 1x in their change line, and they all started out with 0. So their F lines are all going to look the same. And we could fill that in. The hydrochloric acid, on the other hand, we're going to have to take a second and do the math. We're going to do 0.080 minus 2 times this x value. So minus 2 times 0.02229. That gave me 0.03542 moles. And that's how much hydrochloric acid's left over after the reaction is complete. Over here, what do we do here, right? We have a question mark, so how can we finish this? This is our limiting reactant. And we know that for the limiting reactant, our final line has to be 0. So something minus 1x equals 0. Well, we know what x is. X is 0.0229, and we're getting rid of 1x. So we're going to also put that 0.02229 up here. And that's going to give us the 0 that we need in our final line. So this right here, this is probably the most important takeaway from the whole table. This is the amount of calcium carbonate that's in the sidewalk chalk, but we're also going to solve for the other answers. Question A asks us to solve for the mass percent of calcium carbonate in the sidewalk chalk. So I took that initial mole quantity of calcium carbonate from the ICF table, and I used the molar mass of calcium carbonate and determined that that was equivalent to 2.231 grams of calcium carbonate. Now, when I'm doing my mass percent calculation, that value is going to go in the numerator because it's the part. And then the whole thing, the mass of the sidewalk chalk, 3.28 grams, that'll go in the denominator. Grams will cancel grams. Also, because it's a percent, I need to multiply by 100. I rounded my final answer to 2 sig figs because I only had 2 sig figs in the hydrochloric acid information. And that does impact the precision of my final value. So 2 sig figs, I got 68% calcium carbonate in the sidewalk chalk. All right, by mass. So 68% calcium carbonate by mass. So in part B, we're asked to calculate the concentration of hydrochloric acid in that final reaction mixture. So after we're all done and we're ready to clean up, how much hydrochloric acid is in there? And this is an important question to consider. With a reaction mixture like this, it has chalk, water, carbon dioxide. It would be safe to pour down the drain, except you don't want to pour something that's really acidic or really basic down the drain. You would want to neutralize that first. So this is the question to consider so that we know how to neutralize it and dispose of it. So we're going to take, since molarity is moles over liters, we're going to take the moles in our F line for hydrochloric acid, so 0.02229 moles, and divide by the total volume of the reaction mixture, and I'm converting that over to liters in my head because it's moles over liters. And again, we just had 2 sig figs with our initial numbers, so I'm going to calculate the concentration of hydrochloric acid at 0.089 molar. In part C, we were asked to determine the mass of calcium chloride that's present in that final reaction mixture. I took the moles of calcium chloride from my final line and used the molar mass of calcium chloride to determine that we have 2.5 grams of calcium chloride in the reaction mixture. This problem looks similar to the first problem that we did, except here we're after the mass or percent of sodium chloride rather than focusing just on the chloride ion. So we want the mass of sodium chloride, which makes sense because they're analyzing table salt, and we know that table salt is sodium chloride. We were given the mass of silver chloride that was formed. So somehow we're going to have to create a path between the mass of silver chloride all the way to the mass of sodium chloride. Here, I don't think I'm going to use an ICF table. So ICF tables are awesome when we're asked like a gazillion questions. But here, I really just need to solve for the mass of sodium chloride. So that's going to be a lot of extra work for not that much payoff. But if there's multiple questions, then the ICF table is the way to go. What else? So this is based on that same reaction where we have silver ions reacting with chloride ions to form silver chloride. We're leaving out the spectator ions when we write it this way. So nitrate is involved and sodium ion is also involved. However, this doesn't really help me establish the pathway from here to here. So I think for me, I'm going to focus more on the formulas and try to build my path and my bridges that way. Let's start with the 2.044 grams of silver chloride. And grams is not useful at all. So the first thing I'm going to do is get rid of the grams using the molar mass of silver chloride. All right, so the grams of silver chloride are gone. Now we're at moles of silver chloride. So what do I know about silver chloride? Well, I know silver chloride has 1 mole of chloride. So 1 mole of silver chloride has 1 mole of chloride. And I specifically chose to focus on the chloride because that's the ion that both of these things have in common, right? So now I can get rid of the moles of chloride and turn it into the moles of sodium chloride. There's a whole bunch of 1s here. So this may seem kind of redundant, but I have seen situations where it's not necessarily a 1-to-1. You might look at your formula. Oh, it's barium chloride this time. So it's going to be a 1-to-2 or whatnot. So always be careful and always check your ratios. Don't assume that they're going to be 1-to-1. So 1 mole of chloride in 1 mole of sodium chloride. Now to wrap things up, since we want the mass of sodium chloride, I'm just going to tack on a molar mass conversion factor at the end. (58.44 grams). All right, so that leaves us with grams of sodium chloride. That's the value that's going to be in our numerator when we do our mass percent of sodium chloride. So when I did all of this, plugged all of this into my calculator, I got 0.833459 grams of sodium chloride. And then I want to take that answer, my result to this, and divide by the mass of the sample, part over whole. And then I'm going to multiply by 100. How are we doing on sig figs here? So maybe 4 sig figs. We do have a lot of detail in this particular problem. So 98.97% sodium chloride by mass. Makes sense. This is table salt. Like when I purchase table salt, I expect most of it to be sodium chloride. However, if you ever look on the back of the table salt, sometimes it has iodine, and that's not true of all table salt, but some table salt has iodine. And the other thing, when you look at the ingredients, is they usually put like an anti-caking agent in there so that the table salt doesn't stick together.